Hey everybody, Morgan here. Today we're going to be talking about the electrolysis of water, which is pages 9 and 10 of this lecture outline. And the very first time that I was exposed to this was out on the elementary school playground when a kid named Tim, last name will be hidden to protect the maybe not so innocent, was playing around and he showed us a 9-volt battery. And he put it into a cup of water and he poured in a little bit of salt. And we could see bubbles forming on the different posts from the 9-volt battery. And that was kind of an interesting thing, okay? And today we'll be talking about why that electric current is actually able to split the water molecules into hydrogen and oxygen gas. Now, I would typically be doing this in front of you with something called a Hoffman apparatus, so I'll be linking some videos of this demonstration on Schoology. So, if you run electricity through water, you're going to need something to help conduct the current. So we're going to put in some sulfuric acid, although there are other things we can use. Back on the playground, that kid was using just table salt, okay? There are basically 3 reactions that I've put on this page that can happen, and they are right off of your list of standard reduction potentials, okay, highlighted here, printed on your page. So, first off, the liquid water can split into oxygen gas, hydrogen ions, and 4 electrons. EMF's negative 1.23 volts, and the liquid water plus 2 electrons can make hydrogen gas and 2 hydroxides. EMF negative 0.83 volts, and you're about to say, but wait a minute, Morgan. Those are both negative. That's not a spontaneous reaction. Yes, correct. It isn't. You are causing the reaction to happen by putting the electric current into this solution. You are forcing it to happen. Now, you could also have hydrogen ions picking up electrons and turning into hydrogen gas, but that's not going to happen, okay? We have to realize that the concentration of hydrogen ions in water is 10 to the negative 7th molar, okay? So there's just not enough hydrogen ions in there to make this happen, okay? So what is going to happen? Well, first off, 2 H2O liquid is going to give us O2 plus 4 H pluses plus the 4 electrons, and that E naught is the negative 1.23 volts. And then we're going to have to double this reaction to get the electrons. 4 H2O plus 4 electrons, we need those to cancel, is going to give us 2 H2 and 2 OH minus, and that E naught is negative 0.83 volts. Remember, you do not multiply those by a 2 if you multiply the reaction by a 2, and I did a little math boo-boo there. That's a 4. Sorry about that. Okay, now, when I add all this together, 6 H2O, electrons cancel, and that's actually all that's on the left side, gives me O2 plus 4 H plus 2 H2 plus 4 OH minus. Now, I'm going to switch colors here. We're going to acknowledge something. 4H plus and 4OH minus, those are going to react with each other instantly. Strong acid, strong base. And that's going to make 4 waters. And those 4 waters will turn that 6 into a 2. So what I'm really ending up with is 2 H2O liquid to give us O2 gas plus 2 H2 gas. And the E naught for that, we can add those together. Get my calculator here. Negative 1.23 plus negative 0.83, and that's negative 2.03 volts. Okay, now, so continuing on, some electrolyte. Why? It's going to conduct. Pure water will not conduct an electric current. We did some demos about that, which you saw in honors chemistry with light bulbs and different solutions. Okay, now, what does she have to say about this, the standard hydrogen electrode? Okay, so first off, all of these numbers would be based on 1 molar solutions. Okay, now, fact is, the water is about 55.5 molar, very concentrated, so that means Le Chatelier is going to push this reaction over to the right. That's for the water. The H plus is equal to the OH minus, which is equal to 10 to the negative 7th molar, so basically non-existent. I mean, it's there, but not in any concentration for us to worry about that. So, even though the EMF says we need negative 2.03 volts to make this happen, it'll happen at about negative 1.23 volts itself, okay? So, this is a non-standard condition. Even though it's a 25 degrees Celsius, it's non-standard because the water is much more concentrated than the 1 molar that these standard reactions are based on, okay? So now, the EMF is negative. Is that cool? Yeah. We are providing current, or what we might call the driving force, for the reaction to happen. We're pushing it, okay? Now, let's change it up. What if we're not just doing water? So the first video I'm going to put up for you is just electrolysis of water. And you'll notice even in that video that you're going to see 2 parts of hydrogen to 1 part of oxygen. It's really cool, okay? Now, what if we did a solution, and we'll show you one that's a solution also. I don't know if they did sodium chloride. I think it might have actually been sodium sulfate, okay? What species are present? Well, Na plus, Cl minus, H2O, and I'll say H plus OH minus, but they're irrelevant because they're like 10 to the negative 7th molar. This is about 55 molar. And let's assume we're putting in 1 molar sodium ion and 1 molar chloride ion. We can actually get some different reactions happening, okay? So there are 4 possible reactions that can happen, 2 at the anode and 2 at the cathode. Anode's the oxidation, cathode's the reduction. So because of the chloride ions, we could have 2 Cl minus giving us Cl2 plus 2 electrons. And when I go over here and find the chloride reaction, okay, that's going to be a negative 1.36 volts. So E naught equals negative 1.36 volts. And of course the water reaction to H2O liquid to give us O2 plus 4H plus 4 electrons and an E naught that equals negative 1.23 volts. Okay? Now, at the cathode, I could have the Na plus an electron to give me Na. And in fact, this is the way we make sodium. You're not going to find sodium metal in nature. It doesn't exist that way. Okay? Find plenty of sodium ions. We run electric current through it and turn it into that. And that's a negative. I can go to my list here. Okay, it'll be way down here at the bottom. Negative 2.71 volts. Or the water reaction to H2O plus 2 electrons to give me H2 plus 2 OH minus, and that E naught is negative 0.83 volts. Now, theory versus practice. In theory, this reaction and this reaction would happen first, okay? Because they have a smaller magnitude of their potentials, and as we're starting to turn the juice up, these would happen until we run out of the waters, and then the other two would happen. However, it doesn't happen that way in reality. Okay? You have these two competing reactions, and we just see the reality is that the 2Cl minus gives us Cl2 plus 2 electrons. Okay? Now, it's an exception. It happens. Okay? It's part of life. Okay? Explanations as to why evade me. It's what we notice. And remember, experiment trumps theory every time because experiment tells you what really happens. Now here, it's just as we would imagine. The 2H2O plus the 2 electron gives us the H2 and the 2OH minus, and that E naught negative 0.83 volts, which we would imagine would happen because that has a smaller magnitude than that. Okay, look, that's the magnitude. That's huge. That takes a lot of electricity to make that happen. Okay, so I've done this in the classroom by accident, once using HCl rather than H2SO4 as my electrolyte, and man, that chlorine gas smells. It smells something nasty. So there's this term overvoltage, and this is not something that we really understand thoroughly. Okay, there's a lot going on here. Okay, and we say that overvoltage is the amount of electrical energy that must be supplied to make the H2 form instead of Cl2. Okay, this is one of these hand-waving things that we do to try to come up with a definition to or a term to describe something that's really happening. And I don't think that overvoltage is truly thoroughly understood. Okay, I could be wrong on that, but that's the way it was explained when I was in school. Okay, now let's imagine we have, instead of just chloride and water, a mixture of 3 different ions: Ag plus, Cu2 plus, Zn2 plus. Okay, we're going to pass a current through it. Do all of these plate out at the same time, or does one plate out before the other? Now it turns out the first one to plate out is the Ag plus, because that doesn't require a current. That's got a positive EMF. That's going to happen on its own. Okay. Then the next one that would plate out is the copper 2 plus. Also, okay, a positive EMF. All right. And then finally, but you'll notice the Ag plus, it's a larger magnitude. Then finally, the electric current will drive the zinc 2 plus. Okay. To go next. And we get silver metal, and we get copper metal, and we get zinc metal. And we can actually use this as a technique for separating ions in solutions. It's really kind of cool. Okay? All right, so that is pages 9 and 10. This is a topic that I think is really interesting and important to know, except it's not something the AP exam would typically ask a lot of questions about. But still, it's cool material and the type of stuff you need to understand. Okay, thanks for tuning in. This is Morgan signing out.